So let us look at a centrifugal pump. Now these calculations would end up being pretty much the same for an axial flow or mixed flow. It's just centrifugal is a little bit easier to conceptualize because that's what we see the most of. And so if I take a look at this, the fluid comes in here at the eye at point 1. It comes down, it sits there, and it spins around, and then it's ejected at point 2. So now if we assume a steady flow, the pump basically increases the amount of head that's added from point 1 to point 2. So if we draw a control volume around it, and we neglect any heat work or viscous work in the system, we can calculate out the hydraulic power and then the hydraulic head. So if we take a look at this using Bernoulli's equation, pressure over gamma plus V squared over 2G plus Z at the discharge minus pressure over gamma plus V squared over 2G plus Z on the suction side. So the difference between those two is going to give us the Bernoulli head, or H sub P. Now the one thing to remember about this is capital HP. In our energy equation, we've been losing lowercase hp. So when we do the energy equation, we're talking about all the pumps inside the control volume. So if we calculated out HP and we had 3 pumps inside the control volume, this would give us the total head of all 3 of those pumps. So capital HP, we're talking about the specific amount of head just from this one pump. And so if we take a look at that and we sit there and go, well, let's say that 1 and 2 are the same pipe diameter. So basically the velocity at 1 is going to have to be about the same part as 2. And if we say that the height is roughly the same between the 2 of those, we can say that the Bernoulli head of the pump is pretty much just whatever the change in pressure is over gamma. So this is the amount of energy that's imparted by the pump. Now, as we're looking at it, we've talked a little bit about, we've calculated out power before. So that power equation that we used, rho g QH, is really what we call the water horsepower. So the water horsepower is how much, this is what we impart into the fluid. And this is why we've calculated it out before. And so this is based on the Bernoulli head. This is not the power it takes to run the pump, but this is what the pump puts into the fluid. So how do we figure out how much power we put into the pump? Well, this is a rotary dynamic pump, so we have things spinning around, so we transmit power using a spinning shaft. And we've all taken strength of materials at this point, so we know the amount of power transmitted is going to be omega in radians per second times the torque. And so what we call this is BHP, and this stands for brake horsepower. So the water horsepower is how much energy that we put into the system, how much we put into the fluid, and the brake horsepower is how much power it takes to run the pump itself. Now, if we look at that in context of physics, we know that our efficiency is going to be what? Our efficiency is going to be whatever power out we get over whatever power we put into it. And this should always be a number less than 1, because if it's greater than 1, it's over 100%, we've done something wrong. So no matter whenever you're trying to do efficiency, the base efficiency rate is always going to be power out of power in. No matter what system that you're trying to do, no matter what we are doing, it's going to be all the same. So in our case, the power out of a pump that we're getting is that water horsepower, because that's what we're putting into the fluid. What we're putting into the system is going to be the brake horsepower. So now if I look at that, the water horsepower is rho g q, whatever the Bernoulli head of the pump is, divided by omega t. And so this will give us the efficiency of our pump. So if we take a deeper dive into that efficiency, the efficiency of the pump is actually made up of 3 separate things. And so what we have is what we call the volumetric efficiency. We have the hydraulic efficiency. And then we have the mechanical efficiency. And actually what we can do is we can say, well, the overall efficiency is the multiplication of those three efficiencies together. Oops, not equals, multiplies. So what are these different ones? Well, the volumetric efficiency is really talking about fluid loss due to leakage. And so you can actually calculate out the volumetric efficiency by going, okay, well, that's my flow rate over my flow rate plus whatever flow rate of loss that I have. So this is just comes from anything leaking out of the pump and whatnot. I'm going to skip to the mechanical efficiency. So the mechanical efficiency is really just how, that's where you have your loss of all that stuff, friction and whatnot and everything. The important one, or the more interesting one, would be the hydraulic efficiency. And the hydraulic efficiency is made up of three parts. And the hydraulic efficiency is interesting because the way it scales. And we'll talk about this later. The bigger the pump gets, unlike a lot of things that we think is the bigger that we get, the more inefficient that we get. With the hydraulic efficiency, the bigger we get, the better efficiency that we have. So what are these three parts? And the first one's what's called shock loss at the eye. So the eye is the part where the fluid comes into the pump. So shock loss is, and this is specifically in something like a centrifugal pump, where you're coming in straight in, and then all of a sudden you've got to start spinning around. Well, you have shock loss, so that fluid comes in, hits the impeller, and you've got all that momentum going in this direction, and then all of a sudden it's got to stop and start spinning around. The second one we have is friction loss in the blades. And so this is really just the hydrodynamic drag on the impeller blades, slowing things down. And then the last thing we have is circulation loss at the exit. So what circulation loss at the exit is, once again, especially in a centrifugal pump, is it's spinning around and then it goes out. Now, not 100% of that fluid doesn't make it out, because some of it misses and goes back in and starts circulating again until it gets another chance to go out. So we're going to have some small portion of that fluid that's not going to make it out the first time through, and it's going to fill back in and start spinning around again. So we do have these three efficiencies that come together in our main efficiency that we're dealing with. And so typically we're just looking at the mechanical efficiency, which is really just this power in over power out dynamic. But we do have these other efficiencies that can come into play.